Hi everyone, my name is Abel Souza. I'm a postdoc at UMass Amherst. Today I'm going to present Ecovisor, a virtual energy system for carbon efficient applications. We all know we have a sustainability issue. Hyperscale data centers have been doubled in capacity at every 4 years or so for the last decade, primarily due to AI and machine learning workloads. The cloud's energy is already large at around 2% of the world's consumption, and because of this exponential growth, people are worried about its environmental implications. However, the rise in cloud energies is not the main problem. In fact, the issue is the carbon emissions from these energies and its negative impact on the environment. A distinguished characteristic of clean energy is its unreliability. It's intermittent, not available in unlimited quantities at any single location all the time. The former case, the power generated by zero-carbon renewable sources, primarily solar and wind, at any location is unreliable because it varies based on the changing environmental conditions. The latter case, the carbon intensity of grid power is volatile because it varies based on the carbon emissions of the different types of generators the electric grid uses to satisfy its variable demand. But compared to other industries, computing is very well positioned to reduce its emissions by transitioning to cleaner energy sources, despite their reliability. For instance, computation often has significant spatial, temporal, and performance flexibility, and this enables it to shift location time and intensity of execution to better align it with the availability of low carbon and zero carbon renewable. Moreover, computation can also leverage numerous software-based fault-tolerance techniques, including checkpoint and restart, replication, and recomputation. And this can allow applications to continue execution despite unexpected variations in the availability of low-carbon energy, which may require throttling or shutting down servers. But to be able to effectively make use of these characteristics, applications need the visibility into the grid. However, energy operators have traditional and implicitly actually exposed a simple reliability abstraction, the abstraction of a reliable supply of power on demand via the electro socket interface, which is very opaque. Besides, in many cases, the grid system now includes a connection not only the grid, but also an increasingly rich local energy system that also includes energy storage like battery. So the takeaway is that without visibility into the grid's reality, applications cannot really influence how they use their energy and how they can control their compute demand. So our solution is very simple. We propose a library capable to monitor and grant visibility and software-defined control of the energy systems applications through an intermediary API that we call Ecovisor. In this way, applications can have the visibility to monitor the energy and carbon besides the control of where the energy is coming from, such as from the grid, a battery, or nearby solar array. We assume a grid composed of highly energy dense systems, all powered by a combination of renewables and batteries. Applications running on our platform have access to a virtualized energy system that includes a battery, a virtual solar array, and a configurable grid connection with carbon information. This concept is very similar to how applications currently allocate resources in the cloud. And the takeaway is simple. The visibility and control of the energy system will allow applications to monitor energy use and track their emissions to select renewable source when they see fit. So in this figure here, we show the Ecovisor architecture, bridging and exposing real-time energy information by interacting with a container orchestration platform. In our current implementation, we decided to use LXD, which is similar to Kubernetes, but it has more horizontal and vertical scaling features that allow us to better control applications' energy use. The applications then write policies that get enforced through C-group controllers that LXD uses, and it comes with local and cluster support out of the box. So you can run locally, or if you want to scale it up, you can also do that. The control and monitoring functions are exposed to a REST API wrapped around the CO2 signal.com service. It's a third-party service from electricity map that exposes carbon intensity information from various locations around the world and integrate these with the electricity resource management API. And like unique characteristic of our API is that it's very simple and narrow by design. It represents the minimum set of functions necessary to control power and supply, besides demand from application. We chose a container level API to enable the widest range of policies. And more important, developers can use this function to implement higher level interface and libraries that can also further simplify interactions with the virtual energy system or make it entirely transparent to application developers, so they don't really need to worry about taking energy decisions without actually knowing how it works. And to demonstrate the benefits of like this exposition and visibility of the energy system, we deployed a real prototype that emulates low-scale data center using several Raspberry Pis nodes, and all powered from various sources such as the grid and solar, and all accessed through the network and exposed by the Ecovisor. We run several applications and showed them running with two different types of policies implemented in different ways. The first one is a system level policy that are application agnostic and doesn't really use any application information or characteristics to take their decisions. Then we compare this system level policy against application tailored policy that now use application characteristics to take advantage of temporary and workload aspects besides scaling characteristics to allocate resource. In the first experiment, we compared two batch applications, a machine learning training workload and HPC BLAST, which is a bioinformatics application. In this specific experiment, we also compared the system application tailored policy against an agnostic policy that simply executes a job at the time of submission. The system level policy is based on WaitAWhile, which is a middleware paper from 2021, which basically waits for the best period in a carbon trace to submit a job for execution. But the application level policy does the same as WaitAWhile, but besides that, it further scales the application up by 2 or 3 times, or also 4 times in the BLAST case, compared to its original amount of resource. So it uses application characteristics to scale up resource and reduce runtime. So we compare to the runtime and carbon emissions for a system that uses carbon policy that is application agnostic, comparing it against an application tailored policy. So we can see that the Ecovisor allows applications to better optimize their carbon efficiency compared to the system level policy. And like it also enables applications to trade off runtime for carbon emission, besides allowing them to find the optimal scaling factors given the information that we are providing applications with. We next consider application agnostic system level policy that enforces static carbon budget for each application that use rate limiting, or some people also call it carbon cap at all times. So it basically keeps the emissions constant at all times. We compare this policy to an application-specific one that enforces a more flexible budget over longer time periods rather than at all moments of time. The application tailored policy allocates the minimum amount of requests that are needed to meet the SLO. In our case here, it's set at 60 microseconds. This allows applications to breach the cap for shorter periods if necessary. With comparing both, like we show that this dynamic budget policy can help web applications to have better performance during periods when both the carbon intensity and workload intensity are very high. Besides that, on top of the system level policy savings, we achieved 23% higher savings than the system level policy. So, in conclusion, the use of the visibility and control provided by the Ecovisor can provide many benefits in terms of carbon efficiency for different types of applications. By leveraging these exposed functions, applications can make better decisions about their energy use and reduce their carbon footprint. The Ecovisor provides basically it's a foundation for even more carbon efficient applications in the future. For example, higher level libraries can offload this task from applications and which then can be used to develop other abstractions that simplify the development of carbon efficient applications. Our ongoing work is focused on exploiting temporal and spatial flexibility to further reduce carbon and develop new abstractions. I thank you for your attention.